What if the universe is not what we think it is? What if the grand story we've been told about the Big Bang, the birth of stars, and the growth of galaxies is missing its most important chapters? In the summer of 2022, humanity aimed the James Webb Space Telescope into the depths of space, expecting to see the universe in its infancy. Tiny baby galaxies flickering like sparks in a dark void. Instead, what Webb revealed shook science to its very core. Hidden among the stars were colossal giants, galaxies so massive and so complex that they had no business existing in the early cosmos. They weren't faint smudges of light struggling to come together. They were vast, glowing structures packed with hundreds of billions of stars, as if the universe had jumped ahead billions of years on the cosmic timeline. To astronomers, it was like opening a history book about human civilization and finding skyscrapers standing tall in the Stone Age. The laws of physics, the models of galaxy growth, the very timeline of the universe suddenly seemed fragile, uncertain, and perhaps even wrong. These impossible galaxies weren't one-off anomalies. As the telescope collected more data, more of these giants appeared, scattered across the skies like silent challenges to everything we thought we knew. They looked mature when the universe was supposed to be young. They contained heavy elements like carbon and oxygen that should not have existed yet. They even harbored supermassive black holes, so large that their very existence defied the limits of how quickly black holes can grow. The deeper scientists looked, the stranger the universe appeared. Was galaxy formation happening far faster than anyone had ever imagined? Was the universe actually much older than the standard model says? Or, most radical of all, had we been wrong about the Big Bang itself? This wasn't just another discovery, it was a crisis, the kind scientists whisper about but rarely admit in public. A crisis in cosmology. For decades, the Big Bang model has been the foundation of modern astronomy. It told us the universe began 30.8 billion years ago, expanded from a singularity, cooled into simple hydrogen and helium, and only after hundreds of millions of years formed the first stars. But Webb's images suggested otherwise. Galaxies that should have been too young to exist were already thriving. Stars that should have taken billions of years to form were already burning bright, and black holes that should have been tiny seeds were already monstrous giants. Each discovery was like another crack in the story we thought was unshakable. The implications are staggering. If the universe is older, then its history stretches back far beyond what textbooks say. If physics itself was different in the past, then the rules of reality may not be constant. And if the Big Bang is incomplete or even wrong, then humanity's most trusted origin story may need to be rewritten from scratch. But here's the thing, scientists don't agree on the explanation. Some believe galaxies formed under conditions so extreme we can barely imagine them. Others argue that the universe may be twice as old as we thought. And a few whisper about radical alternatives, that space-time and light itself may not behave the way we think they do. What makes this mystery so irresistible is that it's not science fiction. These galaxies are real. The data is real, and every new Webb observation adds fuel to the fire. The cosmos we thought we understood is revealing itself to be far stranger, far more complex, and far more impossible than we ever dreamed. The only question is, are we standing at the beginning of a revolution in science, or have we stumbled into evidence that the universe itself has been hiding secrets all along? On July 11th, 2022, the universe changed forever. The world was waiting for the first official images from the James Webb Space Telescope, the most powerful observatory ever launched, designed to look deeper into space and further back in time than anything before it. Scientists expected to see faint, blurry galaxies, the cosmic equivalent of newborn babies, still wrapped in their first blankets of gas and dust. Instead, they were confronted with something that seemed utterly impossible. Among the data was a tiny red dot, so faint it almost looked like a glitch. But when astronomer Erica Nelson ran the calculations, she nearly dropped her coffee. That tiny speck of light wasn't a primitive galaxy at all. It contained nearly 100 billion stars, making it as massive as the entire Milky Way. The shock didn't stop there. This enormous system was over 13 billion light-years away, which meant Webb was capturing it as it appeared only 700 million years after the universe began. According to everything we know, that should not have been enough time to build something so big, so structured, and so rich in heavy elements. To put this into perspective, galaxy formation is supposed to be a long, slow process. After the Big Bang, the universe was filled with a searing plasma where even atoms couldn't exist. Only after about 400,000 years did the cosmos cool enough for hydrogen and helium to form. For another 100 million years, those elements floated in the dark before gravity started pulling them together into dense clouds that eventually sparked the first stars. Those stars lived short, violent lives, exploding as supernovae and scattering heavier elements like carbon and oxygen into space. Only after several generations of these cycles could galaxies grow into the mature, complex systems we know today. Building something like the Milky Way should take billions of years of recycling, collapsing, and merging. Yet here was a galaxy that seemed to have skipped the entire process. It was already mature, already massive, already glowing with heavy elements, as if the universe had jumped ahead on its own timeline. The discovery sent shockwaves through the scientific community. If this was real, then either our understanding of galaxy formation was completely wrong, or the universe itself was older than we thought. Some whispered about the unthinkable. Maybe the Big Bang model itself needed to be reconsidered. At first, many astronomers assumed this must be a fluke, an anomaly that would disappear once more data came in. But that wasn't what happened. Within months, Webb uncovered dozens more of these impossible galaxies, scattered across the sky like red embers glowing in the cosmic dawn. Each new detection piled on more evidence that this wasn't a mistake. Something fundamental was being exposed. The analogy that scientists used was simple but chilling. Finding a massive galaxy so early in the universe is like walking into a nursery and finding a fully grown adult sitting among the infants. The timeline didn't make sense. By the rules of cosmology, this galaxy should have still been a faint smudge of gas. Instead, it looked like a thriving metropolis of stars, buzzing with activity, filled with heavy elements, and even showing signs of complex structure. How could this have happened in only 700 million years? The math didn't add up. Current physics says that building a galaxy of this size requires at least 2 billion years. That meant one of three things. Either galaxies form in ways we don't yet understand, the universe is far older than 13.8 billion years, or the foundational model of the Big Bang is flawed. None of those options were comfortable, and the most unsettling part. This was just the beginning. That single red dot, that one impossible galaxy, was about to open the floodgates to a cosmic mystery so deep that it would force scientists to question not just their theories, but reality itself. Because once Webb revealed one impossible galaxy, the telescope began finding more. And soon, those discoveries would multiply into a problem so large that no one in cosmology could ignore it. As Webb kept scanning the sky, those first shocking galaxies turned out to be just the tip of the iceberg. Scattered across the darkness were strange objects that astronomers started calling little red dots. They didn't look like normal galaxies at all. Instead of glowing with a range of colors like most star systems, these dots shone almost exclusively in the infrared, burning with an eerie crimson light. To the naked eye, or even to Hubble, they were invisible, nothing but blank space. But Webb's infrared vision revealed them glowing like embers at the edge of time. The more astronomers examined these dots, the stranger they became. Some contained as many stars as the Milky Way, even though they existed when the universe was barely 5% of its current age. Others showed signs of old stellar populations, stars that had been burning steadily for billions of years. That was impossible because billions of years hadn't passed yet. These galaxies seemed to be both ancient and newborn at the same time, defying the very logic of cosmic evolution. The redness itself was the first clue. In a young universe, galaxies should be hot and blue, filled with massive stars that burn quickly and brightly before exploding. Red galaxies usually indicate old age, with cooler stars that have been burning for billions of years. But these red dots were appearing just a few 100 million years after the Big Bang, glowing with the colors of maturity in an era that should have been dominated by youth. It was like walking into a kindergarten classroom and finding students with gray hair and wrinkles sitting among the toddlers. Nothing about it fit the expected timeline. The discoveries multiplied quickly. Instead of being rare anomalies, these red dots appeared in numbers far greater than theory allowed. According to the Big Bang model, only a handful of galaxies of this mass and maturity should exist in such an early universe. But Webb was finding them by the dozens, even by the hundreds. Some estimates suggested they were 100 times more common than predicted. Suddenly, the universe wasn't just producing one or two impossible galaxies, it was filled with them, scattered like cosmic fingerprints pointing towards something deeper and stranger. Scientists quickly split into camps. Some argued that galaxy formation in the early universe must have been far more efficient than we ever imagined. Maybe gravity pulled gas into stars at lightning speed. Maybe dark matter provided extra scaffolding that let galaxies grow faster. Others thought these red dots were illusions created by powerful black holes at their centers. When gas falls into a black hole, it heats up and glows so brightly that it can mimic the light of an entire galaxy, hiding the true number of stars underneath. If that were the case, the red dots might not be impossibly massive galaxies at all, but smaller systems disguised by their blinding cores. But the data didn't let scientists settle on any single explanation. Some red dots did show evidence of black holes, but others contained genuine stellar populations, billions of stars organized into mature structures that simply should not have had time to exist. It wasn't just one theory failing, it was every theory struggling at once. For many astronomers, the red dots weren't just anomalies, they were the smoking gun. The clearest evidence that the story we've been told about the universe's early years was missing something huge. And as Webb kept uncovering more, the mystery deepened. Because the red dots weren't just strange in their light and structure, they also carried hidden signatures of heavy elements like carbon, oxygen, and even iron materials that should have required multiple generations of stars to produce. In a universe only a few 100 million years old, those elements should have barely existed. Yet these galaxies were already rich in them, like cosmic cities with skyscrapers built before the invention of bricks. The contradiction was staggering. The more red dots scientists found, the harder it became to dismiss them as mistakes or illusions. They weren't rare outliers, they were a population, a whole class of galaxies that had no place in the early universe. And if these anomalies were real, then the timeline of cosmic history itself might need to be rewritten. But the red dots were only the beginning. What astronomers discovered next would push the mystery to a breaking point and force them to ask whether the very laws of physics had been different in the early cosmos. The heart of the mystery comes down to time. Building a galaxy isn't supposed to be easy, and it certainly isn't supposed to be fast. In our current understanding, the universe follows a step-by-step process that stretches across billions of years. First, hydrogen and helium must gather into clouds dense enough to ignite the first stars. Those stars burn out quickly, explode as supernovae, and scatter heavier elements across space. Only then can a second generation of stars form, enriched with the building blocks for planets and complex chemistry. Galaxies grow through this slow recycling of matter, colliding with neighbors, merging, and gradually organizing themselves into the sprawling structures we see today. By that timeline, a galaxy as massive as the Milky Way should need at least 2 billion years to take shape. But the James Webb Space Telescope showed us galaxies that looked fully formed when the universe was only 700 million years old. That left just a tiny fraction of the time needed, and yet somehow the universe had already built cosmic giants. The problem isn't just about how fast stars can form. Even under the most efficient conditions, galaxies are thought to be capped at converting only about 10% of their available gas into stars before radiation stellar winds and supernova explosions push the rest away. It's a built-in safety mechanism, a cosmic thermostat that keeps galaxies from burning out too quickly. But the galaxies Webb revealed would have required almost perfect efficiency. Nearly every atom of hydrogen and helium would need to have been converted into stars, leaving nothing wasted. That level of perfection isn't just improbable, it's nearly impossible according to the physics we know. It's like imagining a factory that takes raw materials and turns them into finished products, with zero scrap, zero mistakes, and no lost energy. Nature doesn't work that way. Or at least we didn't think it did. To make matters worse, the heavy elements Webb detected inside these galaxies posed another timing nightmare. Those elements can only be forged inside stars and released when those stars die, which usually takes hundreds of millions, even billions of years. Yet here they were, abundant and widespread in galaxies that should have barely had time for their first stars to even ignite. That meant multiple generations of stars had already lived and died, compressing billions of years of chemical evolution into just a few hundred million. The timeline wasn't just tight, it was broken. This puzzle has forced scientists to consider radical possibilities. One idea is that star formation in the early universe was nothing like what we see today. Maybe stars ignited 100 times faster, or galaxies could somehow bypass the messy cycle of formation and destruction that slows everything down. Another possibility is that the universe itself is older than we think. If the cosmos has been around for not 13.8 billion years, but closer to 26 or even 30 billion, then these galaxies would have had more time to grow. It's a controversial idea, but one that some researchers are beginning to take seriously. And then there's the most unsettling possibility of all, maybe the Big Bang model. The story we've been building science upon for nearly a century is fundamentally flawed. No matter which explanation you choose, the race against time remains the central problem. These galaxies force us to confront a simple but devastating question. How do you fit billions of years of growth into just a few 100 million years of existence? Something has to give. Either the physics of galaxy formation, the age of the universe, or the foundation of cosmology itself. But the mystery doesn't stop here, because hiding inside these galaxies were even more shocking clues, supermassive black holes that had grown far too quickly, challenging our understanding of gravity, matter, and the very limits of cosmic evolution. If the galaxies themselves seemed impossible, the black holes lurking inside them were even more shocking. Astronomers have long known that at the center of nearly every massive galaxy lies a supermassive black hole, a gravitational monster containing millions or even billions of times the mass of our Sun. But building one of these beasts takes time, a lot of time. A typical black hole begins its life as the collapsed core of a massive star, maybe 10 to 100 times the mass of the Sun. From there it can grow by feeding on gas and dust, or by merging with other black holes, but there is a natural limit to how quickly it can feed. This is called the Eddington limit, the balance point where the outward pressure of heated gas pushes back against the inward pull of gravity. Even if a black hole eats as fast as physics allows, it still takes hundreds of millions of years to bulk up to supermassive proportions. And yet, when Webb turned its gaze on those early galaxies, it found clear signs that their centers already contained supermassive black holes. In a universe that should have barely had time to form its first stars, there were already black holes so large they rivaled the ones at the hearts of mature galaxies like the Milky Way. The numbers were brutal. For some of these black holes to exist, they would have had to grow 5 times faster than the Eddington limit, feeding in ways that should be physically impossible. Imagine someone gaining 1,000 pounds by eating only 1 meal a day. That's how absurd the growth rates would need to be. And this wasn't just 1 or 2 cases. Evidence of these primordial monsters appeared across multiple red dots, suggesting the early universe was littered with black holes that shouldn't exist. The very objects that should have taken billions of years to form were showing up only a few 100 million years after the Big Bang. That left astronomers scrambling for explanations. Some proposed that instead of forming from dying stars, these black holes might have skipped that step entirely, collapsing directly out of dense clouds of primordial gas. If true, then the first black holes weren't stellar remnants at all, but direct collapse black holes born already weighing thousands or even millions of solar masses. Others suggested that the early universe might have contained primordial black holes left over from the Big Bang itself. Tiny fluctuations in density collapsing under their own gravity in the very first moments of creation. If those ancient seeds existed, they could have acted as the starting points for the supermassive black holes Webb is now detecting. But even these exotic theories struggle with the sheer speed of growth required. Feeding at 5 times the theoretical limit for hundreds of millions of years straight would demand physics beyond what we currently understand. Some scientists have wondered whether the rules of the early universe were simply different, that the constants we take for granted, like the speed of light or the strength of gravity, might have operated under alternate values in the primordial cosmos. If true, then black holes could have grown faster, stars could have ignited more quickly, and galaxies could have assembled at breakneck speed. It's a radical idea, but Webb's discoveries make it harder to dismiss. Adding to the strangeness, the light from these galaxies revealed powerful quasars, blinding beacons, created when supermassive black holes feed aggressively, heating in falling gas to millions of degrees until it shines brighter than the entire galaxy around it. These quasars were supposed to be rare in the early universe, but Webb found them shining like lighthouses at the edge of time. Their presence didn't just raise questions about how black holes grew so quickly, it also suggested they were playing a massive role in shaping the galaxies themselves, influencing how stars formed and how matter was distributed. The very engines of galaxy evolution were up and running long before they should have even existed. The discovery of these black holes wasn't just a footnote to the story of the red dots, it was a crisis all its own. If the galaxies were already a mystery, the black holes inside them turned that mystery into something far deeper and more unsettling. They weren't just breaking the rules of astrophysics, they were rewriting them. And as astronomers dug deeper into Webb's data, they began to realize that even the idea of what they were looking at might be an illusion. Because some of those impossibly massive galaxies may not have been galaxies at all, but cosmic mirages created by the very black holes at their hearts. As astronomers wrestled with the impossible timelines of galaxies and the even stranger growth of black holes, a new idea began to emerge. What if these galaxies weren't as massive as they seemed? What if some of them were illusions, tricks of light created by the very black holes that seemed to be breaking the rules of physics? At the heart of a feeding black hole is a swirling disk of gas and dust, called an accretion disk, heated by friction to millions of degrees. That searing heat produces radiation so powerful that it can outshine billions of stars combined. In fact, a single quasar, A galaxy with an active black hole at its center can blaze brighter than an entire cluster of galaxies. From Earth, that kind of brilliance makes it almost impossible to tell what's underneath. A galaxy that looks like it contains 100 billion stars might actually have only a fraction of that, its light artificially inflated by a ravenous black hole blazing at the center. It's like walking into a dark room, shining a spotlight into your own eyes, and then trying to count the candles in the background. You simply can't separate the glare from the reality. This mirage hypothesis offered a tempting way out of the impossible early galaxy problem. If many of Webb's red dots weren't actually massive star-filled galaxies, but smaller systems made to look enormous by their central quasars, then the laws of physics might not be broken after all. The galaxies would still be impressive for their age, but not outright impossible. It was a neat solution, one that seemed to reconcile observation with theory, at least on the surface. But the deeper astronomers dug, the less convincing the mirage explanation became. Spectroscopic analysis, splitting the light into its component wavelength to read the chemical and stellar signatures, showed that many of these galaxies weren't just bright. They carried the fingerprints of large stellar populations, heavy elements, and complex structures. These weren't just gas clouds being lit up by a central monster. They were genuine galaxies with billions of stars, galaxies that had formed too fast and too early. The mirage hypothesis could explain some of Webb's findings, but it couldn't explain them all. Even when astronomers stripped away the blinding light of black holes, many galaxies still appeared far too massive for their place in the cosmic timeline. And that raised an even deeper question. If some of the red dots were illusions, but others were real, how do we tell the difference? Were we looking at a mix of genuine ancient giants and tricksters hiding behind their own glare? The uncertainty only made the mystery more profound. It meant that the early universe wasn't simply breaking the rules in one consistent way. It was breaking them in multiple overlapping ways. Some galaxies were impossibly massive, some contained impossibly fast-growing black holes, and some looked like both at once. The mirage idea did more than complicate the mystery. It forced scientists to confront the possibility that their instruments, powerful as they are, might still be deceiving them. Webb is the most advanced telescope humanity has ever built, but even it is limited by distance, faint light, and the distortions of cosmic time. The further back we look, the harder it becomes to untangle what's real from what's projected, exaggerated, or hidden by the universe itself. It's a sobering reminder that even with all our technology, the cosmos still has ways to blind us. But for many researchers, the persistence of genuinely massive galaxies, even after accounting for the mirage effect, pointed to something deeper. The early universe might not just be producing illusions, it might be operating on rules we don't yet understand. The idea that the red dots could be a combination of reality and illusion only underscored one unsettling truth. Whether we're seeing genuine impossibilities or cosmic tricks, both point to gaps in our knowledge of how the universe really works. And as Webb kept returning more data, another radical idea resurfaced from the forgotten corners of cosmological history, an idea that questioned whether the universe was even expanding at all. Long before the James Webb Space Telescope began sending back its impossible images, a controversial idea had been buried in the margins of cosmology, a theory that most scientists dismissed decades ago. It was called tired light, and it proposed something radical. What if galaxies aren't actually racing away from us? And what if the universe isn't expanding at all? Instead, what if light itself loses energy during its long journey through space, slowly stretching into redder wavelengths the further it travels? This idea was introduced in the early 20th century as an alternative to the Big Bang. According to tired light, the redshift we observe, the key evidence for an expanding universe, could simply be the aging of photons over billions of years, not proof that space is stretching. For nearly a century, this theory was considered fringe, unable to explain critical observations like the cosmic microwave background. But then Webb revealed galaxies that seemed far too mature to exist so early in cosmic history, and suddenly tired light didn't look so dead anymore. If tired light is true, then the red dots we're seeing are not galaxies caught in their infancy, but systems billions of years older than we think. They've had all the time they need to form stars, build heavy elements and grow black holes. The problem of impossible early galaxies simply disappears, replaced with a universe that has been around much longer, possibly twice as long as Big Bang cosmology suggests. Some researchers now argue that the universe could be 26 or even 27 billion years old, not 13.8. That would mean the timeline we've built, the timeline that places the Big Bang as the beginning of everything, may only be half the story. Of course, tired light comes with its own problems. It struggles to explain why distant galaxies appear smaller in the sky than nearby ones, something the expanding universe model accounts for easily. It also doesn't naturally explain the cosmic microwave background, the faint afterglow of radiation that permeates space, a cornerstone of Big Bang cosmology. To fix this, some scientists have tried combining tired light with new twists, like allowing the fundamental constants of physics to change over time. If the speed of light, the strength of gravity, or other constants have shifted since the early universe, then the physics that governs galaxy formation might not have been the same back then as it is now. That could explain why stars and black holes grew faster, while tired light handles the redshift puzzle without invoking expansion. For critics, these explanations sound like bending over backward to save a flawed theory. But supporters argue that Big Bang cosmology already asks us to accept invisible concepts like dark matter and dark energy, which make up 95% of the universe yet have never been directly detected. If we can embrace those mysteries, why not entertain the possibility that light itself ages, or that the constants of nature are not constant at all? The James Webb discoveries have cracked open the door to ideas that were once ridiculed, forcing scientists to revisit old theories with new urgency. What makes tired light so compelling now is how neatly it resolves the early galaxy crisis. If the universe is older, there's no rush. Galaxies had billions of extra years to grow, stars had time to cycle through multiple generations, and black holes had the breathing room they needed to bulk up without breaking the laws of physics. Suddenly, the impossible becomes inevitable, and that's why this once discarded theory is creeping back into scientific debates. Webb didn't just challenge our view of galaxy formation, it shook the very foundation of time itself. But tired light, even if it solves one problem, raises countless others. If the universe isn't expanding, then what does that mean for the Big Bang? Did it even happen at all? If not, then where did the cosmic microwave background come from? Why does the universe look the way it does today? And if space has always existed in roughly the same state, what does that mean for our understanding of beginnings, endings, and the ultimate fate of everything? These questions remind us that solving one mystery often opens the door to a dozen more. And just when tired light began to gain traction again, another unsettling possibility emerged. What if the rules of physics themselves weren't fixed, and the early universe played by an entirely different set of laws? If the galaxies Webb uncovered are real, massive, and ancient beyond explanation, then perhaps the problem isn't with our telescopes or even with our timelines. It may be with the very laws of physics themselves. For generations, scientists have treated constants like the speed of light, the strength of gravity, and the charge of the electron as immutable. They are the bedrock of equations, the unchanging rules written into the universe's fabric. But what if those constants weren't truly constant? What if, in the early universe, physics played by different rules? This radical idea has been gaining traction, not because astronomers want it to be true, but because the data seems to demand it. To explain galaxies that appear fully formed in less than 1 billion years, something fundamental must have been different in that primordial era. Take star formation, for example. In today's universe, the birth of stars is a slow and inefficient process, limited by cooling rates, gas density, and feedback from stellar winds. But what if gravity was stronger in the early cosmos? That would mean gas clouds collapsed more quickly, igniting stars at breakneck speeds. Or what if the speed of light was slightly higher? That would affect how energy radiated, how matter cooled, and how structures condensed. Even a tiny shift in these constants could completely reshape the timeline of cosmic evolution, compressing billions of years into hundreds of millions. Suddenly, galaxies that seemed impossible begin to make sense, not because our models were wrong, but because the rules of the game were different. Of course, changing physics is a dangerous idea. It challenges one of science's deepest assumptions, that the laws we measure here on Earth are universal, the same everywhere and everywhen. If they are not, then the entire foundation of cosmology shakes. Imagine if gravity's strength shifted slightly across billions of years. Every model of star formation, galaxy growth, even planetary orbits would need rewriting. Yet the galaxy's Webb has shown us force this unsettling possibility back into the spotlight. They are either breaking the rules or revealing that the rules were never fixed in the first place. Some researchers are already proposing models that combine tired light with variable constants, creating a universe not 13.8 billion years old, but closer to 26 or even 30 billion. In such a cosmos, not only do galaxies have more time to evolve, but the physics of the early universe accelerates their growth. It would be a double solution: more years on the cosmic clock and faster processes to fill those years. The elegance of this explanation is undeniable, but so is its controversy. Because if constants can change, then science itself must accept that nothing is absolute. Critics argue that this idea is a slippery slope. If physics isn't fixed, then how can we trust any equation, any model, any theory? But supporters counter that we already accept unknowns like dark matter and dark energy, placeholders for forces and substances we can't see. Why should we draw the line at variable constants? After all, nature has surprised us before. Once we believed the Earth was the center of the universe. Once we thought the cosmos was eternal and unchanging. Each time, new evidence shattered those beliefs. Now, Webb may be pointing us toward the next revolution. The realization that the universe evolves not just in structure, but in its very laws, and the implications are staggering. If the constants that govern the universe can change, then reality itself is not fixed. The physics we measure today may not be the same tomorrow. The cosmos may be a living, evolving system, rewriting its own rules as it grows. For some, that is too unsettling to accept. For others, it is the only explanation that fits the evidence in front of us. But no matter where one stands, one thing is clear. If the laws of physics are not eternal, then our understanding of reality is incomplete. And just as this radical thought takes hold, another tool emerges from the shadows: computer simulations that attempt to replay the universe's history and test whether any of these wild ideas could truly account for Webb's impossible galaxies. When the data from James Webb began pouring in, astronomers turned to one of their most powerful weapons against mystery: simulations. These digital universes are like time machines, allowing scientists to start with the conditions of the early cosmos and let the laws of physics play out across billions of years inside supercomputers. If galaxies as massive as the Milky Way could really form in less than 1 billion years, the simulations would show how. If not, the discrepancy would expose just how wrong our theories might be. But the first results were grim. Using standard physics, gravity, gas dynamics, and star formation rates, the simulations simply could not reproduce the galaxies Webb was seeing. Instead of vast, mature giants, the computer universes gave birth only to tiny, chaotic systems, faint smudges of light compared to the colossal red dots captured by Webb. It was as if reality itself had broken the code of physics, while the simulations remained trapped in a universe that should exist, but clearly doesn't. That failure forced researchers to rewrite their models, injecting new possibilities into the equations. What if the early universe was denser and more turbulent than we imagined? What if gas clouds cooled more efficiently, collapsing faster to form stars? What if galaxy mergers were not rare, but constant and violent, smashing small systems together to create giants at record speed? With these modifications, something remarkable began to happen. The simulations started producing galaxies that looked suspiciously like Webb's red dots. Not only did they glow brightly, but they also showed signs of rapid starbursts, brief, furious episodes of creation where galaxies converted nearly all of their gas into stars in just a few million years. It was like watching cosmic cities rise overnight, skylines of stars emerging far ahead of schedule. The models also revealed the role of dust, a subtle but powerful player. When stars are born and die, they scatter dust grains that absorb blue light and re-emit it in red and infrared. Webb's infrared eyes are particularly sensitive to this glow, meaning that galaxies rich in dust could appear older and more massive than they really are. A galaxy experiencing an intense starburst might generate enormous amounts of dust, tricking our instruments into seeing it as a giant filled with mature stars. In other words, some of Webb's impossible galaxies might not be impossibly old. They might simply be cloaked in cosmic smoke, giving the illusion of ancient maturity. But even as simulations offered possible solutions, they raised new questions. If violent mergers and starbursts created these galaxies, why are there so many of them? Webb has revealed hundreds, maybe thousands, far more than models predict even under extreme conditions. And if dust is fooling us, why do spectroscopic tests confirm that many of these galaxies really do contain heavy elements, carbon, oxygen, iron, that take multiple generations of stars to forge? The simulations could mimic the appearances, but they struggled to fully replicate the chemistry. That disconnect hinted at something deeper, suggesting that while simulations are powerful, they are only as good as the rules fed into them. If those rules, our physics, are incomplete, then no amount of computational power will ever match reality. Still, the advances from these digital universes proved invaluable. They demonstrated that, under the right conditions, galaxies could form faster than we ever imagined, perhaps not violating physics, but pushing it to its breaking point. They showed that dust and starbursts can create illusions, complicating our interpretation of Webb's images, and they suggested that the early universe was a place of chaos and violence, where galaxies collided and merged in a cosmic frenzy unlike anything we see today. Yet even as simulations closed some gaps, others remained wide open. The impossible galaxies were still out there, still too massive, still too early, still too advanced, and that meant astronomers would have to look beyond computers and equations for answers, turning instead to the oldest light in the universe itself, the cosmic microwave background, the afterglow of creation, which might hold the final verdict on whether our understanding of the cosmos is fundamentally broken. Long before the James Webb Space Telescope shocked the world with images of impossibly massive galaxies, scientists already had what they considered the most solid piece of evidence for the Big Bang, the cosmic microwave background, or CMB. This faint glow of radiation discovered in the 1960s is often described as the afterglow of creation, the leftover heat from when the universe was just 80,000 years old. At that moment, the cosmos had cooled enough for atoms to form, allowing light to travel freely through space for the first time. Today we see that light stretched into microwaves by billions of years of cosmic expansion, a uniform sea of radiation that fills the entire sky. To cosmologists, the CMB is the crown jewel, the proof that the Big Bang happened just as textbooks describe. Its tiny variations in temperature, measured with astonishing precision by satellites like WMAP and Planck, map out the seeds of galaxies and clusters, matching the predictions of standard cosmology with almost eerie accuracy. For decades, the CMB was untouchable, the evidence that silenced doubters. But then Webb arrived, and suddenly the unshakable foundation began to look less certain. The problem is simple but devastating. If the early galaxies Webb observed really existed at those distances and masses, they imply that the universe was forming complex structures far earlier than the CMB predictions allow. According to the Standard Model, it should have taken hundreds of millions of years after the CMB's release for stars to form, then more time for galaxies to grow, and much longer for them to reach the maturity Webb is showing us. Yet there they are. Galaxies filled with heavy elements, organized structures, even signs of black holes, all within a cosmic blink after the CMB was supposedly set in stone. It is as if the map of the seeds and ripples encoded in the CMB is out of sync with the galaxies we now see. If the CMB is the script, then Webb's discoveries are actors who have gone completely off book. This has led some researchers to consider the unthinkable, that our interpretation of the CMB itself might be flawed. Could it be that the nearly perfect glow across the sky is not what we think it is? Proponents of alternative theories like tired light suggest that if photons lose energy over distance rather than being stretched by expanding space, then the CMB might not be a direct remnant of the Big Bang, but rather the cumulative radiation of stars and galaxies blurred and redshifted beyond recognition. Others go further, proposing exotic interactions between photons and particles that could mimic the CMB we see today without requiring a singular explosive origin. To mainstream cosmologists, these ideas border on heresy, but Webb's data has forced them back onto the table. And the CMB presents another puzzle. Its near-perfect uniformity across the sky shouldn't be possible if the universe is only 13.8 billion years old. Some regions of the sky are so far apart that light could never have traveled between them in the time allowed, yet they show the same temperature down to millionths of a degree. This horizon problem has long been explained by cosmic inflation, a brief period of faster-than-light expansion in the universe's first trillionth of a second. But inflation is still a theory, not a directly observed fact, and Webb's impossible galaxies have made some scientists wonder if inflation was simply a bandage on a deeper misunderstanding. If the CMB's smoothness and Webb's early giants both defy the standard timeline, then perhaps both are symptoms of a bigger problem, that the universe's age, structure, and physics are not what we assumed. None of this means the CMB is fake. It's there, it's real, and it tells us something profound. But what exactly it tells us may no longer be so clear. If it is not the afterglow of the Big Bang, then what is it? If it is, then how do we reconcile it with galaxies that appear billions of years older than the timeline permits? These questions hang like a shadow over modern cosmology, forcing scientists to consider that the most sacred evidence of the Big Bang might not be the final word. And as debates swirl, Attention turns to the darker side of the universe itself, the mysterious invisible matter that makes up most of its mass. Because if the early galaxies are real, then the dark matter scaffolding that was supposed to build them has some explaining to do. The discoveries made by the James Webb Space Telescope have done more than expand our vision of the cosmos. They have shaken the very ground beneath the feet of modern science. For nearly a century, cosmology has been built on a foundation that seemed unbreakable. The Big Bang, cosmic expansion, the steady growth of galaxies over billions of years, and the familiar rules of physics guiding it all. But the appearance of massive, mature galaxies just a few 100 million years after the supposed birth of the universe has torn cracks through that foundation. These galaxies are not supposed to exist. They are too big, too heavy, too chemically enriched, and too structured for their time. And yet, there they are, glowing like ancient cities in the dawn of time, mocking our certainty and daring us to rewrite the story of creation itself. The implications are staggering. Either the universe forms galaxies in a way we never imagined, with star formation rates and efficiencies so extreme they push physics to its breaking point, or our entire timeline of cosmic history is wrong. Perhaps the universe is far older than we think, stretching back not 13.8 billion years, but 20 or even 30 billion, giving galaxies the time they need to mature. Or perhaps the Big Bang itself, the crown jewel of modern science, is not the full story. Alternative models once dismissed as fringe, like tired light or cyclic universes, are resurfacing in serious debate. The impossible galaxies have forced cosmologists to reconsider ideas that were long locked away in the shadows, reminding us that science is never finished, never final, and never immune to revolution. What makes this crisis so profound is that it touches every corner of cosmology. The cosmic microwave background, once considered untouchable evidence of the Big Bang, now looks out of sync with Webb's galaxies. Dark matter, the invisible scaffolding meant to explain galaxy formation, struggles to account for the rapid appearance of giants. Supermassive black holes that should take billions of years to grow appear fully developed in the cosmic dawn, breaking the limits of gravity itself. Every solution offered, whether exotic starbursts, dusty illusions, or radical new physics, creates new problems in turn. It is as though the universe is telling us that we have only been reading the first draft of its story, and the real narrative is far stranger, far more complex than anything we have dared to imagine. But perhaps the greatest revelation is not about galaxies or timelines, but about ourselves. For centuries, humanity has tried to impose order on the cosmos, weaving neat theories that fit the evidence we can see. Each discovery has given us confidence, the sense that we are closing in on the truth, and yet, time and again, the universe has humbled us, showing that what we thought was complete was only a fragment of the whole. Webb's galaxies are the latest reminder that the cosmos is not bound by our expectation. It is bigger, older, wilder, and stranger than the rules we write in our textbooks. To stand under the night sky today is to know that we live in a universe that refuses to be simple, that laughs at the idea of final answers, and that always holds its deepest mysteries just beyond the reach of our imagination. As Webb continues its mission, peering further into the past and deeper into the unknown, we can only wonder what new impossibilities await. Will it confirm that the universe is twice as old as we thought? Will it reveal physics that rewrite the very constants of nature, or will it uncover something so unexpected, so unimaginable, that it forces us to rethink the meaning of reality itself? The impossible galaxies are not the end of the story. They are the beginning of a new chapter in humanity's search for truth. A chapter where every answer raises more questions, where certainty dissolves into mystery, and where the universe itself seems to whisper that the journey of discovery has only just begun.